This is the ALU of my homebrew 8-bit CPU. It has an 8-bit adder which takes the left-hand side and the right-hand side input, adds them together, and produces a result. It can also shift the left-hand side input left or right before it gets fed into the adder, but it can't really do logic operations at the moment. The only thing we have is a bunch of XOR gates on the right-hand side to conditionally invert the right-hand side for subtraction. But we want to do more than that. We want to be able to compute the AND or XOR and maybe some other operations between the left and right-hand side input of the ALU. And I like the arrangement we have here. We have the adder as the core component, and then we have a shift box in a sense on the left-hand side, which can do various kinds of shifting. And on the right-hand side, currently it's just the inverter, but on the right-hand side we can have a logic box, which can do various kinds of logic operations before stuff gets fed into the adder. And that gives us a lot of flexibility. When we want to do shifts, we set the right-hand side of the adder to 0 through this new logic box we're going to build, and that will make the shifted version of the input pass through the adder. And when we want to do some logic operations, we'll set the left-hand side input of the adder to 0 through this shifter here. It already has this option. It has a 0 mode where it injects a 0, which will pass whatever logic operation we do on the right-hand side through the adder. Now we want to be able to compute a whole bunch of logic operations here on the right-hand side. So we definitely don't want to have dedicated AND or XOR and other chips down here and then select between them, because that's going to be a whole bunch of chips that we need to add. Ideally, we'd have a circuit that accepts a truth table, basically the 4 values for all combinations of input bits, and which produces the corresponding output. One neat way to go about this is to use a 4-input multiplexer, because that multiplexer has 2 select signals, which corresponds to 2 input bits, and then you can basically set the output of that multiplexer for each of the combinations of input bits by configuring the 4 inputs that are being multiplexed. If you've seen James Sharman's fantastic 8-bit CPU series, he uses exactly this approach in his ALU. The downside is that these 4-way multiplexer chips that we've used in other places of the ALU here, they actually have 2 multiplexers in one chip, but the 2 multiplexers share their select input signals. That means that for a lookup table, you can only use one of the multiplexers in the package. So you'd end up with 8 of these multiplexer chips to do logic operation on 8-bit inputs. I'm going to use a slightly different approach. I'm going to use 2 more of these programmable logic devices, these ATF16V8B chips here, that we've already used for the decoding in the previous episode. Big shout out to Eric, who has proposed this approach in the comment section of the previous episode. So we want a circuit that can perform any 2-input logic operation. That means its truth table is going to have 4 entries, 1 for each combination of input bits. And by setting these 4 entries of the truth table, we can configure what kind of operation it should perform. And since there are 4 entries in this truth table, there are 16, 2 to the power of 4, different logic operations that you can perform. If all bits in the truth table are 0, you'll get a 0 at the output, regardless of what the inputs are. Truth table 0001 produces a 1 as a result when both sides are 0. That is a NOR operation. 0010 produces a 1 if the A input is 0 and the B input is 1. So that's not A and B. 0011 doesn't depend on the B input, which you can see because there's a pair of zeros and a pair of 1s. When the A input is 0, this is going to produce a 1, and when the A input is a 1, this is going to produce a 0. So this inverts the A input. Truth table 0100 produces a 1 exactly when A is 1 and B is 0, so this computes A and not B. 0101 is independent of A, which you can see because the top and the bottom 2 bits in the truth table are identical. This produces a 1 when B is 0, or a 0 when B is 1, so this effectively inverts B. Truth table 0110 is just the XOR operation. 0111 is a NAND operation. 1000 is a AND operation. It produces a 1 exactly when A and B are both 1. 1001 is the inverse of the XOR. It's a NOT XOR or an XNOR gate. 1010 is again independent of the A input, and it is a 1 whenever B is a 1 and a 0 otherwise. So this just passes through B unchanged. 1011 produces a 1 at the output when either A is 0 or B is 1. So this computes effectively not A or B. 1100 is independent of B, and it produces a 0 when A is 0 and a 1 when A is 1. So it just passes through the A input unchanged. 1101 produces a 1 when either A is a 1 or B is a 0. So this computes A or not B. 1110 is just the OR operation between the two sides. And if all bits in the truth table are set, you will get a 1 as a result, regardless of what the input bits are. So this is basically like a constant 1 operation. And these are all the logic operations you can do with a 2-input logic gate. Some of these are clearly useful. For example, I think we want an AND operation, an OR, and an XOR operation. And it's probably also useful to have a 0 operation, so we can set the right-hand side input to a 0. But some of the other operations here might be a bit more niche. But it's good to have them available, and we can just define new instructions that access those. So let's go take a look at how we can program this ATF16V8B chip, which we've used in the previous episode to do the decoding, to also do these logic operations and to basically implement this configurable truth table. Let me copy the PLD file we've created for the decoder and let me call it logic.pld. Let me change the name and the description. Let me pull up the datasheet for the ATF16V8B such that we know what pins we have available. And I think we want to put this into the breadboard such that the top part here of the chip faces the left-hand side input and the bottom part faces the right-hand side input. And so it would be convenient if the first 4 inputs on the left here are going to be the RD bits, and the other 4 bits of input here are going to be the RS inputs. And we're not going to use the clock. And then on the right-hand side, we have a bunch of pins available that can be either inputs or outputs. And since we're only dealing with 4 bits of the input, we only need 4 outputs on this chip, and we can use the other 4 pins here as the input where we feed in the truth table, the logic operation that we want to perform. Now pins 15 and 16 are a bit weird. When we look at the description of the simple mode and we look at the diagram for one of the I/O pins on the right hand side, you can see that it says that pins 15 and 16 are always enabled, which refers to this multiplexer switch over here, and that pins 15 and 16 do not have this feedback path. And what that basically means is that pin 15 and 16 are always an output, and there's no way for us to take whatever's on pin 15 and 16 and feed it back into the logic grid. So for us, that means that whatever we do, pins 15 and 16 should be part of the output of kind of the computed logic results, and we can't use 15 and 16 as an input where we feed the truth table. But that's not too bad. If you look at pin 11, 12, 13, and 14, there are 4 potential input bits down here, which we can use for the logic operation. So let's do that. And then afterwards we can use pins 15, 16, 17, and 18 as the output of the logic operation, where we basically produce whatever the truth table produced that we configured. We do have a spare pin here, pin 19, which we're not using, so let's just skip that. And then the final pin is VCC. Okay, let's think about how we can actually implement this truth table logic. Get rid of the datasheet and the old logic equations. And now we can assign a bunch of logic terms here, a disjunctive normal form, to each of the outputs. And I think the easiest way for us to go about this is to write down a separate term in the DNF for each of the different combinations of input bits. So essentially each line here corresponds to a certain set of inputs. And now we have the inputs L0, 1, 2, and 3, which correspond to the output column of this truth table. And since the AND gates on the left here produce a 1 hot encoded signal, basically one of the AND gates, the one corresponding to that line in the truth table, is a 1 and all the others are 0, we can just AND each of these AND gates with the corresponding truth table bit, which will essentially cause these AND gates to pick one of the truth table bits and produce that as a result. And so this is basically a 4-way multiplexer expressed as a disjunctive normal form Boolean expression. For each of the different RD and RS input bit combinations, we're forwarding one of the truth table bits, L0, 1, 2, or 3. Now we don't just have one output, but we have 4 of them, so let me add a few zeros. And let me collapse this onto a single line. And now we can just copy paste this for the other 3 outputs. Great, that should be all that's needed. Let me run this through the Galette compiler and let's see what output it produces. Seems to be happy. Let's look at the files that it produced. This is the pinout of the chip, which is basically what we configured. We have 4 bits of the left-hand side RD inputs, 4 bits of the right-hand side RS input. We take the 4 truth table bits as an input, and we produce 4 output bits, which are essentially the truth table applied to pairs of the RD and RS input bits. Let me write this configuration to 2 fresh new ATF16V8B chips, and then let's add them to the breadboard and hook them up. Let me get started by removing the XOR chips on the right-hand side here. And then let me place the 2 chips we've just programmed. Then let me connect power and ground. And let me add 4 LEDs to show what the truth table is that we're feeding into these chips. Pins 11, 12, 13, and 14 are the logic operation inputs. Let me connect those between the chips and also to the LEDs. The right-hand side RS inputs are on pins 9, 8, 7, and 6. Let me bring those over all the way to the right such that we have a clear place where we can plug in the right-hand side from the CPU. And the left-hand side RD input is on pins 5, 4, 3, and 2 of the chip. Let me bring those over all the way to the left-hand side. We're going to plug in the left-hand side input from the CPU here, and we also need the left-hand side up here for the shifting, so let me add these connections here. And finally, the outputs of the logic operation are on pins 15, 16, 17, and 18. Let me connect those over to the right-hand side input of the adder. And that's all there is to it. Let's give this a quick test. I'm going to set the upper 4 bits of the left-hand side to a 1 and the lower 4 bits to a 0. These chips have pull-ups on their inputs, so I just need to connect the zeros. And I'm going to set bits 1, 2, 5, and 6 of the right-hand side to a 1 and all the others to a 0. Alright, so we have 2 fixed values on the RD and the RS input of the ALU. We can see the logic operation we pick here, and we'll be able to observe the result of the logic operation up here at the right-hand side input of the adder. Nothing catches fire, that's pretty good. Let's try a few truth table inputs. First, let's try 1010, which is the RS operation that just passes through the right-hand side. This looks good. You can see the right-hand side I've connected show up here at the adder input. Let's try the NOT RS operation, which is going to show the inverted pattern. This is operation 0101, which also works. We can also pass through the left-hand side input with operation RD, which is a 1100, which also works. The left-hand side input has the upper 4 bits set to a 1 and the lower 4 bits set to a 0. And we also have a NOT RD operation, which does the opposite, show us the inverted version of the left-hand side. This is operation 0011, which also works. This is the inverted left-hand side input. We can also produce an all ones value by setting all bits of the logic operation to a 1, which works. And the opposite, we can set all bits of the logic operation to a 0, which produces a 0 value. And so regardless of the left and right hand side inputs, we'll get a 0 at the output of the logic block. Let's try a few logic operations. For example, let's try AND, which has the truth table 1000, which works. As you can see, the output bits are set whenever the left-hand side input bit and the right-hand side input bit are set. We can also do the OR operation with truth table 1110, which works, and an XOR with truth table 0110, which also works. There are also the inverted versions of these. For example, we can have an XNOR operation with the truth table 1001, which works. It's the exact opposite than what we had before. We can have a NOR with the truth table 0001, which also works. And we can have a NAND with the truth table 0111, which also works. Pretty cool, that seems to be working. By setting the truth table input of the logic block down here, we can perform arbitrary logic operations between the left and right hand side, which we are going to produce as an output, which is going to be the right hand side input of the adder here. The only thing left to do is to connect the logic operation input down here to the ALU decoder up here, such that we can pick a logic operation when we're decoding the ALU op and configure what the right hand side does. Now the only thing left to do is to go in and update this ALU decoder chip and add a few operations that make use of this new logic capability down here. Let's go take a look. Let me open up that decoder text file that we've been using to derive the logic functions of the decoder. To make this a bit easier to work with, let me rearrange the columns a bit and let me add the operation names for the carry and shift operations. And now we no longer have this right-hand side inversion signal. This is now a fully fledged 4-bit truth table that we can feed into the logic block of the ALU. Let me rename this to logic operation, and let's go through the table and update this. When we're doing an addition, we want to have the right-hand side RS input to be passed through unchanged, so we need the RS logic operation. When we're doing a subtraction, we want to have the right-hand side RS input inverted, so we need the NOT RS logic operation. For the NOT and negate operations, we've been reading the RS register, doing the operation on that, and then writing the result into the RD register. But I think it would be more in the kind of general vibe of this 8-bit CPU if these unary operations would just read the RD register, which comes in through the left-hand side, do their operation, do their inversion and negation, and then write back to the RD input. So instead of taking the RS input and inverting it, let's actually take the RD input and invert it in this case. So that's the NOT RD operation. And when we're doing shifts, we want to set the right-hand side input of the adder to a 0. So we'll want to use the 0 logic operation here. Note that we've been relying on pull-down resistors in the circuit to actually pull the right-hand side to a logical 0 thus far. But now with this logic operation, we can actually be very explicit about it and force the adder's right-hand side input to a 0 properly. So that's the existing operations updated. But now that we have this logic operation that we can do an arbitrary truth table, we can do other operations. So let's define an AND or an XOR operation. For these logic operations, we want to set the left-hand side input of the adder to 0, and we also want to make sure that we are not injecting a carry into the adder, so both the carry operation and the shift operation need to be 0. And then the truth table for an AND operation is 1, 0, 0, 0. Let's also add an OR, and the truth table here is 1, 1, 1, 0, and an XOR, which has the truth table 0, 1, 1, 0. We need to pick new opcodes for these operations. Let's maybe start at the bottom. Let's make XOR number 15, or number 14, and number 13. This way the logic operations are at the bottom and we still have a gap between the shift and the AND operation in case we come up with other operations. So time to come up with new logic expressions. Let me get rid of the old ones first. And then let's start at maybe logic operation 0. Logic operation 0 is this column here, and we're interested in all the entries of this operation table where this column here has a 1. So in these 4 lines, the logic expression that we're going to write needs to produce a 1, and it needs to produce a 0 in all the other cases. So let me copy the ALU opcode bits, which are the input to the decoder, and let's translate this into a disjunctive normal form. These two opcodes are identical except for the last bit where we have a 0 or a 1. So essentially we don't care what the last bit needs to be. We're going to produce a 1 either way. And the same down here. We don't care what the last bit is. Let me delete the duplicate lines. These now represent individual terms in our disjunctive normal form, which we can just type up. Let's do logic operation bit 1 next. We need to produce a 1 whenever we see one of the opcodes in the selected lines. Let me get rid of the irrelevant inputs. And let's type that up as a Boolean expression. Next up, logic operation bit 2. And logic operation bit 3. And notice again that we cannot collapse these two lines because they not only differ in one position, but in two positions. That's all our logic operations. Let's do the same for the shift operations. And since we haven't used opcode 1011, we can use it to optimize this expression some more. And this is exactly this not F2 expression we had in the previous episode, because this shift operation bit 0 is basically just the inverted version of the opcode bit number 2. And we can play the same trick here. And finally, the carry operation. And that looks pretty good. These are the new logic expressions that we need to program into the decoder. And then hopefully, whenever we pick one of these opcodes, the corresponding output operations for the logic operation, shift operation, and carry operation are going to be picked. Let me copy this over into the decoder PLD file. And let's also update the pin assignments. Because this invert right-hand side signal is no longer there, but we now have logic operation 0, 1, 2, and 3. And that should be it. Let me compile this with Galette. And let's go take a look at the pinout. We still have our ALU opcode inputs. We still have the carry operation and shift operation. But now we also have this logic operation output that we're producing, which is essentially a truth table for what happens with the right-hand side input to the adder. Let me get the 16V8 decoder chip out of the ALU, and then let's write this updated configuration to it. Let me quickly check a few of the opcodes. ALU operation 0 is an add, which sets the logic operation to RS. That works. Operation 2 is a subtraction, which sets the logic operation to not RS, which also works. ALU operation 4 is the not operation, which sets the logic operation to not RD, which also works. ALU operation 6 is a shift left logical, which sets the logic operation to 0. That works. Operation 13 is the AND operation, which sets the logic operation to AND. That works. Operation 14 is OR, which sets the logic operation to OR. And operation 15 is XOR, which sets the logic operation to XOR down here. So this looks like it might just work. Let me get the CPU back out, and then let's reintegrate the ALU into that and write an updated program to make use of these new features of the ALU. Let me reconnect power. Then we need the clock and the output enable, and the right-hand side and left-hand side inputs. We also have the result of the ALU that needs to go back to the registers, and we need to connect the ALU operation to the instruction bits. And that's all there's to it. Let's go and update the instruction set architecture and add instructions for the new operations that the ALU can do, and then update the assembler and write a new program. We've added the AND, OR, and XOR ALU operations. And now let's update the instructions. First of all, we slightly changed how NOT and negate, the unary operations, work. They no longer take an RS register operand, but they just take the RD register operand. And they will read RD, do the inversion or negation, and then write back to RD. So this slightly changes the encoding. Let me set the RS field in the instruction to all zeros. And let me get rid of the RS operand. And now let's add an AND, OR, and XOR instruction that triggers the corresponding functionality in the ALU. And that's the updated instruction set architecture. Let's go and update the assembler. And as expected, the assembler isn't happy with our changes yet, so let's go fix that. First, we need new opcodes for AND, OR, and XOR. Then let's go and fix the parser. NOT and negate no longer accept the second register, they just have the RD operand. And we have a bunch of new instructions to parse. Then let's fix instruction printing. And finally, we need to make sure that the assembler can encode the instructions. NOT and negate no longer need to encode their second operand because that's gone. And we have the new instructions that we need to encode. And that should be it. Let's see if the test file works. Yeah, that looks good. If I scroll up a bit, you can see that NOT and negate have this new format. They just take a destination register and the encoding has changed. And we now have the AND, OR, and XOR operations here with a corresponding encoding. And I think at this point we can just go and update the ALU test program and make use of the new instructions. First of all, since we've changed the encoding for negation and it would be good to test the negation, let me copy over the negation test from a previous program we've written. So that uses the new format for the negate instruction. And down here we have a NOT instruction, which we also need to update. Let me also clear register R2 at the top here, because we've been setting that in the negate test. And then all the way at the end here, instead of halting already, let's actually try out the AND, OR, and XOR instructions. Let me load the same bit pattern into R0, 1, and 2, such that we can do AND, OR, and XOR on it. And then let me load a different pattern into R3. Just going to set the upper 4 bits to 1 and the lower 4 bits to a 0. This will be similar to the patterns we use during hand testing of the logic circuitry. And at this point, let's just do an AND, OR, and XOR operation. Let me quickly write down what the expected pattern is. And then at the end here, let me clear R3 again, and then let's just halt the processor. Pretty nice. Let me assemble this program and write it to the program memory. First up, we're going to clear the register file. And now we're going to negate numbers. First, we'll load the number 1 into R0, the number 10 into R1, and the number 100 into R2. And now we're doing a negate instruction on register R0. You can see that the ALU is set to the negate operation, which the decoder converts into the NOT RD logic operation. So this operation is going to negate the 1 in register R0 to -1, the 10 in R1 to a -10, and the 100 in R2 to a -100. Perfect, that works like a charm. Next up, we're going to do a subtraction with add and not instructions. First, we're going to clear register R2, and then we're going to load 24 into R0 and 19 into R1. To do the subtraction, we're going to invert the bits in register R1. We're using a NOT operation for this, and you can see the ALU operation is set to NOT, which the decoder converts into a NOT RD operation down here at the logic block. And indeed, the logic block inverts the left-hand side input, presents it up here. This is the exact inverted bit pattern of what's in register R1, and this gets produced as the ALU's output, which gets stored in the register file again. So when I hit the clock, we're going to see this register's bits flip. And now we're going to take the value in that register R1 and we're going to add it to register R0. And you can see on the ALU we have the add operation selected, which is going to set the logic operation to just RS, such that the right-hand side is passed through completely unchanged. Now we're going to load the value 1 into R1, and we're going to add that into R0. And that looks great. This is the value 5, which is indeed 24 minus 19. And we were able to do that subtraction not with the subtraction operation, but with a separate add and not operation, which we now have available in the ALU through this new logic block down here. Now we're going to do a simple division by 4 by using an arithmetic right shift. We did this already in the previous episode to test this new shift right arithmetic instruction. We're going to test it again just to make sure that the logic operation down here is decoded properly. First, we're going to load the value 84 into R0. And then we're using a shift right arithmetic on R0. And the ALU is set to the shift right arithmetic operation, and then as expected the logic operation is set to a 0 because all the shifting happens up here in the shifter on the left hand side path, which as you can see does the right shift properly, and we don't want to do anything on the right hand side, we just want to pass in a 0 such that we're not disturbing this shifted result, and that seems to be working properly. So when I hit the clock 2 times, we're going to see the bits in register R0 shift to the right by 1 place, effectively dividing by 2 and by 2 again. And indeed, 84 divided by 4 is 21. Let's do this with a negative number. We're going to load minus 84 into register R1, and we're going to do 2 right shifts. And this indeed leaves the value minus 21 in register R1, which is minus 84 divided by 4. And now we're going to try a few logic operations. First, we're going to load a bit pattern into register R0, R1, and R2. And then another bit pattern into register R3. And now we're doing an AND operation. We're ANDing the value in R0 with the value in R3. And indeed, the ALU is set to the AND operation, which the decoder converts into the logic operation AND. As you can see, this is the AND truth table down here. And importantly, we're setting the shift operation to 0, such that the left-hand side of the adder is 0, and we're setting the carry operation to 0, such that we're not injecting a carry. So effectively, this disables the entire left-hand side and carry side of the ALU's adder here, and just passes the result of the logic operation through to the output. And indeed, the ALU's result is the AND operation between registers R0 and R3. Then we're doing an OR operation between register R1 and R3. The ALU is set to the OR operation, which is decoded properly into the OR truth table here at the logic operation. And indeed, the result of the ALU is the bitwise OR between registers R1 and R3. And finally, we're going to do an exclusive OR between registers R2 and R3. The ALU is set to the XOR operation, which is decoded into the XOR truth table down here. And indeed, the result of the ALU is the XOR of the values in R2 and R3. That's perfect, that seems to have worked. So we have successfully executed an AND, OR, and an XOR operation, and now the processor has arrived at the halt instruction and the program is officially over. This is very exciting, we're getting very close to finishing the ALU. Not only can it do addition and subtraction with and without carry, it can also do logic operations like inversion, AND, or XOR. And it can do unary operations like taking the left-hand side and converting it to its negative form, or taking the left-hand side and shifting it to the left or to the right, and again with an optional carry version and an arithmetic version. And this will already allow us to write pretty complicated programs. Having AND, OR, and XOR available unlocks a lot of powerful new algorithms and things we can do with the CPU. In the next episode, I think I'll want to look at the flags that we have in the ALU. Currently, we only have a carry flag, which conveniently is produced by the adder, but there are other flags that are interesting that we might want to use. For example, we might want to detect if the result is a 0, if the operation we did caused an overflow internally, or just look at the sign bit of the result and store that into the flags register. And having a few more flags available is going to be interesting to use for condition codes in instructions. For example, you can have a conditional jump that looks at the current state of the flag bits and performs the jump or doesn't perform the jump, depending on whether a flag is set. And similarly, I think we could try to do a conditional move in the ALU here by looking at the flags. And then depending on whether a flag is set or not set, we use the logic block down here to either forward the left-hand side RD input or the right-hand side RS input to the result. But to do that, we need a few more flags to make it more powerful, and I think that's something we'll do next time. Thanks a lot for watching, like and subscribe if you want to see more of this, and see you next time.